Welcome to the debate. I want you to imagine for a second trying to understand a riot in a crowded theater.
Okay.
You have the structural layout of the building, right? So the stage, the aisles, the concrete walls, and then you have the frenetic, unpredictable movement of the crowd itself.
Right. The actual chaos of the situation.
Exactly. And to the naked eye, the architecture of the space and the panic of the people, it just blurs into one singular, unreadable event. It's overwhelming. And usually when we talk about observing a complex, chaotic system, there's this expectation that the chaos is just inseparable from the environment it happens in.
It is overwhelming, absolutely. I mean, we like to think we can track individual movements and, map everything out neatly, but in reality, the sheer volume of interaction makes it feel impossible to separate the container from what's actually contained inside it.
Yeah.
You're watching the whole system just heave and shift all at once.
But what if you could perfectly peel them apart? Like, what if you had a mathematical tool that could extract the fixed architecture of that theater on one side, and then completely isolate the dynamic chaos of the crowd on the other?
That's a big what if.
It is, but that is precisely the ambition of a recent 2026 working paper. They're applying what's called the Continuous Time Vector Complex System Response Framework. We'll just call it the CSR framework.
Yeah, CSR is easier.
Right, and they're applying it to the classic Lorenz system. And I'm looking at this paper as a revolutionary operational paradigm, because by translating those classic three-dimensional equations of chaos into this new CSR language, the authors have figured out how to reorganize messy, continuous time dynamics into these highly structured, experimentally interpretable layers.
Mm-hmm.
They're essentially making deterministic chaos rigorously measurable, which is why I'm arguing that this framework is a genuinely practical blueprint for the lab.
Well, I will certainly acknowledge the analytical beauty of what this paper achieves. I mean, I look at this from a much more cautious angle, though. The mathematical translation of the Lorenz system here it's undeniably elegant.
Yeah.
However, that perfect separation of the geometry of the system from the gain or the amplification of the system, I think it's an idealized mathematical artifact.
Really?
Yeah, because the authors are relying so heavily on a pristine, zero-variance mathematical playground. The classic Lorenz model it's incredibly clean.
Sure.
But in my view, that cleanliness obscures the messy, inextricably coupled reality of true multivariable systems that scientists actually have to deal with in real laboratories.
Well, I think we need to look at exactly why this mathematical translation is such a breakthrough before we dismiss it as just a toy model. For a long time, mapping the controllable parts of a system to its emergent chaotic properties has been just a massive headache.
Oh, absolutely.
So what the authors have done is they translate those standard equations into a new mathematical space, a coefficient tensor space.
Right.
And by doing this, they achieve something remarkable. They definitively separate the fixed structural interactions of the system from the way the system amplifies its own states.
They pull the geometry and the gain apart.
Exactly. If you look at how the Lorenz system is built in this new framework, the underlying interaction structure, those specific quadratic interactions, the negative xz and the xy.
Yes, the classic nonlinearities.
Right. Those are entirely locked in place. They never change. Meanwhile, the control parameters, so your sigma, your rho, your beta, the knobs you can turn to add heat or change the flow, those alone move the system from stability into chaos.
And that works beautifully on a chalkboard.
It's more than a chalkboard exercise, though. I mean, his framework provides an exact end-to-end map. It takes you all the way from the first moment a system becomes unstable, right, like the exact pitchfork boundary at rho equals 1, right up to exact Hopf surface, culminating in this unified 6-layer chaos certificate. I mean, it's an unprecedented blueprint for taking something wildly unpredictable and making it accountable to measurement.
Let me just jump in there, because the concept of an unprecedented blueprint is exactly where I get held up.
Okay.
Achieving these precise mathematical milestones, like the Hopf crossing at 470/19, in a simulation is a stunning feat. But we have to remember why the Lorenz equations were chosen as the benchmark for this paper in the first place.
Because they're the gold standard of chaos theory?
Well, yes, but specifically because their reduced, incredibly simplified quadratic structure allows for the component Hessians to remain perfectly constant.
Okay, yes.
There is zero structural variance in this model. So going back to your analogy, the theater walls never budge a millimeter.
Right.
But if you step into the real world, if you're dealing with real thermal convection or a physical laser or a biochemical feedback loop in a living cell, the structural geometry and the local amplification, they're never perfectly separated. They're always bleeding into one another.
I see the concern about applying a pristine model to a messy lab. I do. But let's dive straight into the actual metric the paper uses to address this exact issue. The geometry gain index?
GG.
Right, the IGG. This index is really the empirical engine of the whole framework. Instead of just assuming the system is neatly separated, it gives you a simple equation to measure it.
Right.
It's the variance of the Jacobian divided by the variance of the Jacobian plus the variance of the Hessian plus a small noise floor parameter, epsilon.
Yes, epsilon.
So the index looks at how much variation is coming from the actors dynamically moving around versus how much variation is coming from the stage physically warping. And because the pure Lorenz system has a perfectly fixed stage, the Hessian variance, that VH term, is exactly zero.
Exactly zero, yeah.
Which yields an IGG of 1 or 100%. Meaning the chaotic dynamics are entirely driven by the actors changing speed and direction, not by the floorboards moving.
Right.
So this index gives experimentalists a mathematical tool to prove, using their own data, whether their system is undergoing a fundamental structural rewiring or simply a change in how the components are moving across the same architecture.
I understand the theory behind the ratio. I really do. But I have to push back on how practical it actually is.
Why? It's derived directly from the data.
Because that theater analogy works beautifully in a mathematical vacuum. But in a physical experiment, the stage is constantly warping. You're talking about a metric that requires the structural variance, the Hessian variance, to be perfectly zero to get that clean 100% reading.
Yeah.
But the moment you introduce real-world sensors, experimental confidence intervals, measurement noise, that VH term is going to fluctuate.
Sure, there's always noise. Right, but in a real biological loop, the interactions aren't purely simple and quadratic. There are hidden, higher-order complexities. There are measurement thresholds. So when a researcher is staring at their data, trying to figure out if their system just underwent a massive structural rewiring, like a Hessian inertia switch, or if it's just the natural noise of the gain fluctuating, the signal is going to be completely obscured.
But the paper elevates a mathematical tautology of a pure system into a diagnostic tool. But nature simply does not provide that level of purity.
But wait,
That is exactly why the authors didn't just write a pure mathematical ratio. They included that specific noise floor parameter, the epsilon, in the denominator of the index. They are mathematically anticipating the very measurement thresholds you're worried about.
I know they include epsilon, but the index isn't demanding absolute purity from nature. It operates as a bounded metric to tell you whether the variance in your system is overwhelmingly driven by amplification or by actual structural deformation. Furthermore, the framework explicitly separates out situations where the structure gets dangerously close to vanishing into the background noise. They created a distinct flag for that scenario. They know physical sensors have limits, and they built a buffer into the formula to prevent the index from spitting out wild, misleading results just because of a little static in the data.
Look, a mathematical buffer is a nice safety net. But anticipating noise mathematically and actually resolving it experimentally are two very different beasts.
I mean, they're related.
They are, but adding a small parameter to keep a fraction from blowing up to infinity doesn't magically clarify whether a living cell is rewriting its genetic pathways or just temporarily boosting its protein production. The noise floor just keeps the math from breaking. It doesn't necessarily reveal the biological truth.
Well, I would argue it gives you the best possible lens to search for that biological truth. But let's look at how the framework handles time and deformation, because I think this is where the operational power really shines. We've talked about the spatial layout, the stage, but chaotic systems are constantly evolving in time.
Right, the trajectory of the chaos.
Exactly. The paper introduces this concept of a finite time CSR deformation gradient. and they use Liouville's formula. Think of it like injecting a tiny, perfectly round droplet of ink into a swirling, turbulent river, and just watching how that droplet stretches and squishes over time.
Okay.
The framework uses established physics principles to reveal a completely exact, constant volume contraction budget. The divergence is exactly negative, sigma plus 1 plus beta.
Right, the trace of the Jacobian.
Yes. What that means is, in this system, the chaotic stretching is perfectly balanced by an overarching compression. When you sum up the forces pulling the ink apart and the forces squishing it together, they equal a precise, unchanging constant.
Which flawlessly matches the theoretical predictions of the model?
Yes, and if you look at the canonical parameters, 10, 28, and 8/3.
Mm-hmm.
The system has this persistent stretching, this sensitive dependence on initial conditions, which gives us the butterfly effect. But every ounce of that chaotic stretching is strictly financed by an even stronger contraction elsewhere in the system.
Right.
It shrinks the overall volume of our metaphorical ink droplet down to zero over an infinite amount of time, while still maintaining the chaos inside it. Yielding that Kaplan-York dimension of 2.062. It maps the deformation incredibly clearly. It shows us exactly how chaos sustains itself without simply exploding into infinity.
It is a phenomenal ledger. I won't argue that. But I have to ask, have you considered that this perfectly constant, unchanging ledger of expansion and contraction is an exceedingly rare, highly specific property of this exact set of equations?
Well, it's a property of dissipative systems.
Sure, but the exact constancy of it. The authors state that their long-term goal is to use this tool on forced or adapting systems in the real world, right? That translational outlook.
Yeah, exactly.
But in any real dynamic environment, you have parameter drift. The underlying rules of the system are subtly changing over time. The temperature in the room shifts, the chemical gradient degrades, the laser fluctuates.
Okay, yes, real systems drift.
So the stretching and squishing will not sum up to a neat, perfectly constant -41/3 ledger. That clean budget breaks down the moment the system stops being perfectly stationary. So while this deformation budget is a pristine diagnostic for a computer simulation, I see it falling apart when applied to the noisy, drifting time series data of an actual multivariable system.
I have to challenge that, because it sounds like you're assuming the authors are naive to the realities of a laboratory.
I don't think they're naive,
Because if you look at what they call their data sufficiency hierarchy in Table 1, they explicitly outline architectural provisions for those messy, non-stationary systems. The framework actively accounts for environments that drift.
How so?
It doesn't tell a researcher, just assume your biology experiment is perfectly stationary. It says if your system is being forced by outside influences, you must augment your state space. Meaning you track those external forcing phases or hidden physiological changes as if they were variables in the system itself.
Okay.
They even mandate that any model you build has to be validated against out-of-sample trajectories to specifically catch the parameter drift you're talking about.
Look, augmenting the state space is a very standard theoretical fix. But think about what that actually means in a lab. You're telling an experimentalist to just capture the latent, hidden variables that are forcing the system.
If they want to use the framework, yeah.
But that assumes you have incredibly high-resolution, multi-directional data to accurately estimate those hidden parameters without catastrophic errors propagating through your math.
Well, you need good data, yes.
In a three-dimensional computer simulation where you control everything, sure, augment the state space. But what happens in a complex biochemical network where there are 10 dimensions of interaction, but your sensors can only physically measure 3 proteins?
Right.
At that point, trying to calculate an exact tangent deformation budget becomes highly speculative. You're balancing a ledger with missing receipts.
That's a fair point about missing variables. But isn't that exactly why establishing this benchmark on a pristine model is so necessary in the first place?
What do you mean?
Before we take a completely novel framework into the mud of a biology lab, we have to prove that the core calculus works flawlessly across every possible state of a known system. We have to know the engine works before we drive it off-road. And that brings us to what I consider the ultimate synthesis in this paper, the 6-layer chaos certificate.
Oh, the grand finale.
The grand finale, exactly. This is where the framework builds a bridge from continuous, flowing time into discrete, step-by-step logic. And the way they do it is just brilliant. They use an upward Poincaré section.
At z equals rho minus 1.
Right, where the derivative of z is positive. So imagine putting a turnstile at a specific checkpoint in our chaotic theater. Instead of trying to track every sweeping movement of an actor, you just record every time they pass through the turnstile. Do they go left? Do they go right?
The symbolic itinerary.
Yes. By tracking those successive intersections, they map the continuous flow into an expanding, one-dimensional map. They generate a symbolic itinerary, literally just a sequence of lefts and rights based on which wing of the chaotic attractor the system visits.
The classic left-wing, right-wing switching that the Lorenz system is so famous for.
Precisely. And they take that empirical, data-driven sequence, measure its metric entropy, which comes out to about 0.903, and they marry it to one of the most famous mathematical proofs in chaos theory, Tucker's robust strange attractor proof.
Right, from the early 2000s.
Yeah. Tucker basically built an inescapable mathematical fence using rigorous interval arithmetic around this system, proving once and for all that the chaos is genuine and won't just fizzle out or wander off to infinity. So by combining the data-driven turnstile measurements with this deep mathematical proof, the authors achieve a robust, deeply layered chaos certificate. It starts at the very bottom with local spectral bifurcations, scales up through the deformation budgets we just talked about, and reaches all the way to global, mathematically proven invariant objects. I mean, it is a completely airtight protocol for certifying deterministic chaos.
I will completely agree that the 6 layers represent a phenomenal list of achievements.
Okay.
But I have to heavily question the utility of this certificate as a forward-looking protocol for new discoveries. The 6-layer certificate is, in many ways, a highly sophisticated repackaging of classical dynamics.
Repackaging.
Let's look closely at that final layer you mentioned, Tucker's mathematical fence. That proof is a deeply established, highly specialized mathematical achievement that is perfectly tailored to the exact known equations of the Lorenz model.
Yes, it is the gold standard.
It's the gold standard for that specific system. But you cannot simply export Tucker's custom-built fence and drop it around a beaker of unknown fluid.
Well, obviously you can't just...
In the paper, the authors point to their data-driven turnstile metrics, specifically looking at sequences of binary words, tracking all the possible left and right combinations up to a sequence length of 5.
Right, the block complexity curve.
Yes. And we have to be honest about what that actually is. 32 combinations of left and right coin flips is a finite sample diagnostic. It's a neat numerical observation. It is not a rigorous mathematical invariant set theorem for an unknown biological system.
No, it's not a theorem, but...
The framework borrows the theoretical authority of Tucker's proof to make its empirical data look airtight. But in a real lab, discovering a new chaotic system, you won't have Tucker's proof backing you up. You'll just have a short list of finite word counts, and that is simply not enough to certify global chaos.
Okay, I see why you might think they're just borrowing authority. But I would argue they are doing something much more profound than that.
Which is?
The paper isn't claiming you can magically export a bespoke mathematical theorem into an unknown beaker of chemicals. What they're doing is calibrating their instruments. They are aligning their empirical, data-driven metrics, like the finite sample word counts and the deformation budgets, with the rigorous theorems in the one benchmark environment where we absolutely know the theorems hold true.
So it's a calibration exercise.
Exactly. If the left and right sequence data perfectly matches the unbreakable mathematical fence in the Lorenz benchmark, it proves the metric is trustworthy. It gives experimentalists massive confidence that when they take these same empirical tools into the wild, where the invariant sets and the mathematical fences are completely unknown, the tools will act as reliable proxies.
I see.
It builds a hierarchy of evidence. You can't always get to layer 6 in a messy lab, but you can certify the chaos at the highest level your data supports, knowing the underlying methodology has been proven against the gold standard.
I completely agree with the concept of building a hierarchy of evidence. And, calibration is essential for any scientific tool. My caution is simply against hubris.
Hubris.
Yes, the mathematical autopsy performed on the equations in this paper is exquisite. The precision is unmatched. But elevating that autopsy to the level of a rugged experimental protocol is highly ambitious. Because it relies so heavily on fixed structural stages, constant volume ledgers, and bespoke mathematical proofs. I fear this framework might remain a beautiful theoretical benchmark. It could become a mathematical museum piece, rather than a rugged, dirty tool for the real world, where geometry and gain are always dancing together, permanently bleeding into one another in ways we can barely measure, let alone perfectly separate.
It is a valid caution, I'll give you that. To summarize my position, though, I truly believe this framework operates as an unprecedented analytical Rosetta Stone.
Right.
By mapping exact local boundaries, the exact moments a system sparks from stability into instability, directly to measurable real-time budgets of stretching and folding, it provides a highly structured protocol. It gives scientists a way to monitor physical systems, where the underlying nonlinear mechanisms might only be partially understood. It manages to isolate the structural architecture from the dynamic amplification in a way that is mathematically unassailable, giving us a clearer lens on chaos than we have ever had before.
And to summarize my view, while I deeply respect the sheer exactness of how this paper separates the structural components from the chaotic amplification, I believe the friction of reality will severely complicate its application.
Yeah. The pristine nature of the benchmark model allows for an exactness that experimentalists will almost never actually observe in their data. The transition from pure calculus to noisy, multivariable laboratory experiments is fraught with drifting parameters and coupled dynamics. Ultimately, I think this framework may struggle to untangle those complexities in practice.
Yet, despite our disagreement on its immediate readiness for the messy laboratory, I think we both converge on the immense theoretical value of this work.
Oh, absolutely.
Viewing complex, chaotic systems through the lens of explicit, mathematically isolated layers, rather than just staring at a tangled mess of data, it forces a level of rigor that this field desperately needs to move forward.
I agree. It demands that we stop treating chaotic systems as impenetrable black boxes. It forces us to start rigorously accounting for exactly where the stretching, the folding, and the unpredictability are actually coming from, even if nature doesn't always provide us with a perfectly rigid stage to measure it on.
So we return to our crowded theater. Thanks to this framework, we now have a mathematical blueprint that tells us exactly how to map the concrete aisles and exactly how to measure the chaotic flow of the crowd.
Right.
But the ultimate test of this blueprint won't happen on a clean chalkboard. It's going to happen in the noisy, imperfect, fluctuating laboratories of future multivariable experiments. Will the mathematical ideal survive translation into the friction of reality, or will the architecture and the riot remain forever blurred?